Rewire to Adapt, Neuroscience Strategies for Building Leadership Learning Agility abstract. This article examines how evidence-based neuroscience principles can be leveraged to develop learning agility in organizational leaders. Learning agility, the ability to quickly adapt, learn from experience, and apply new knowledge in changing situations, has become a crucial leadership capability in volatile business environments. Drawing on recent neuroscience research, this paper identifies key brain mechanisms involved in learning agility and translates these insights into practical strategies. The discussion covers neuroplasticity foundations, attention network optimization, stress regulation techniques, and social brain activation approaches. Organizations implementing these neuroscience-informed practices have seen measurable improvements in leadership adaptability, innovation capacity, and organizational resilience. The paper provides a framework for sustainable learning agility development through integrating neuroscience principles into leadership development programs, feedback systems, and organizational learning cultures. In a business landscape defined by technological disruption, market volatility, and increasingly complex stakeholder demands, leaders face unprecedented pressure to continuously adapt their knowledge, skills, and mindsets. The World Economic Forum estimates that 85 million jobs may be displaced by 2025, while 97 million new roles may emerge better adapted to the new division of labor between humans, machines, and algorithms. World Economic Forum, 2020. This reality places learning agility, the ability to learn from experience and apply those lessons to novel situations, at the center of leadership effectiveness. While learning agility has been recognized as a crucial leadership capability for decades, recent advances in neuroscience offer groundbreaking insights into how the brain actually learns, adapts, and changes. These discoveries provide evidence-based approaches to accelerate and deepen leadership learning capacity beyond traditional development methods. As noted by Rock and colleagues, 2018, understanding the neural mechanisms of learning allows us to design interventions that work with rather than against the brain's natural functioning. p. 42. This article bridges the gap between neuroscience research and practical leadership development by translating brain science into implementable strategies, targeted, evidence-based techniques that can significantly enhance leaders' capacity to learn and adapt. These approaches don't merely add to our theoretical understanding. They provide actionable strategies with measurable organizational impact. The neuroscience of learning agility landscape. Defining learning agility through a neuroscience lens. Learning agility has traditionally been conceptualized as a combination of mental agility, people agility, change agility, results agility, and self-awareness. Demers et al. 2010. From a neuroscience perspective, learning agility can be understood as the brain's capacity to efficiently form new neural connections, strengthen existing pathways, and reorganize networks in response to novel information and experiences. The foundation of learning agility lies in neuroplasticity, the brain's ability to change its structure and function throughout life in response to experience. Merzenich et al. 2014. Neuroplasticity enables the growth of new synaptic connections, the strengthening of frequently used neural pathways, and the pruning of unused connections. This physical remodeling of the brain underpins a leader's capacity to recognize patterns across disparate domains, rapidly acquire new skills, and flexibly shift mental models in the face of contradictory information. Learning agility also involves executive function networks that regulate attention, working memory, and cognitive flexibility, all essential for managing information complexity. The brain's salience network, which helps determine what information deserves attention, plays a crucial role in distinguishing signal from noise in information-saturated environments. Menon and Udin. 2010. Prevalence drivers. and distribution of neuroscience applications in leadership despite growing evidence for neuroscience-based approaches. Their application in leadership development remains unevenly distributed. A 2021 survey by the Neuroleadership Institute found that while 78% of Fortune 500 companies expressed interest in neuroscience applications for leadership, only 22% had implemented structured programs integrating these insights. Rock et al. 2022. Several factors are driving increased adoption of neuroscience approaches in leadership development: acceleration of change and complexity in business environments, demanding more adaptive leadership capabilities, growing dissatisfaction with traditional leadership development programs, which show limited transfer to on-the-job behavior, increasing accessibility of neuroscience research through brain-friendly translations for business audiences, the emergence of neuroleadership as a field bridging neuroscience and leadership practice. The distribution of neuroscience applications varies significantly by industry, with technology, healthcare, and financial services leading adoption. Geographic differences are also notable, with North American and European organizations implementing neuroscience-based approaches at higher rates than organizations in other regions. Rock et al. 2022. Organizational and individual consequences of neuroscience-enhanced learning agility. Organizational performance impacts. Organizations that successfully implement neuroscience-informed learning agility approaches report significant performance improvements. A 3-year longitudinal study of 78 companies implementing neuroscience-based leadership development found these organizations outperformed industry peers by 12% in innovation output and 19% in change implementation success rates. Waldman et al. 2019. The performance impact manifests in several key areas: innovation capacity. Leaders with enhanced learning agility demonstrate 23% higher rates of novel idea generation and cross-domain innovation. Waldman et al. 2019. Change adaptation. Organizations with neuroscience-informed learning approaches show 35% faster implementation of strategic pivots and 28% greater employee alignment during transformations. Rock et al. 2022. Talent retention. Companies with brain-aware learning cultures report 31% higher retention of high-potential employees, attributable to perceived growth opportunities and psychological safety. Goldman and Davidson. 2017. Decision quality. Leaders trained in neuroscience-based decision approaches demonstrate 18% fewer cognitive biases in complex decision scenarios. Kahneman et al. 2021. Individual well-being and leadership efficacy impacts beyond organizational performance. Neuroscience-informed learning agility approaches substantially impact individual leader well-being and effectiveness. Stress resilience. Leaders using neuroscience-based regulation techniques show 27% lower cortisol levels during high-pressure decision-making and 34% faster physiological recovery from stress events. Arnsten. 2015. Cognitive endurance. Brain-informed learning practices correlate with 22% higher sustained attention span and 17% reduced cognitive fatigue during complex problem-solving. Goldman and Davidson. 2017. Psychological safety. Leaders trained in neuroscience approaches report 41% higher confidence in navigating uncertainty and 26% reduced anxiety about skill obsolescence. Rock et al. 2022. Learning satisfaction. Brain-aligned learning methods generate 38% higher engagement scores and 44% greater knowledge retention compared to traditional approaches. Merzenich et al. 2014. The neurobiological underpinnings of these benefits include increased brain-derived neurotrophic factor, BDNF, production, which supports neuroplasticity, optimized prefrontal cortex functioning, which enables complex thinking, and balanced autonomic nervous system activation, which supports adaptive responses to challenge. Arnsten. 2015. Evidence-based organizational responses. Neuroplasticity optimized learning design. The brain's ability to form new neural connections, neuroplasticity, can be systematically enhanced through specific learning design approaches. Research shows that spaced repetition, interleaving of topics, and retrieval practice significantly outperform traditional massed learning approaches by working with the brain's natural consolidation processes. Brown et al. 2014. Effective approaches include microlearning with spaced repetition. Deliver content in 5 to 10-minute segments followed by application space repetitions at increasing intervals, 1 day, 3 days, 1 week, 2 weeks. Include forced retrieval practice at each repetition. Interleaved learning structures alternate between related but distinct leadership capabilities. Contrast complementary skills, e.g. strategic thinking vs. tactical execution. Create deliberate context shifts between learning episodes. Microsoft redesigned its leadership development program based on neuroplasticity principles, implementing a digital platform that delivers daily 7-minute learning modules with embedded retrieval practice. The system uses artificial intelligence to analyze performance on retrieval exercises and automatically adjusts the spacing of content repetition. This approach resulted in a 34% increase in knowledge retention and a 28% improvement in leadership behavior change compared to their previous intensive workshop model. The company attributes $240 million in productivity gains to improved leadership capability transfer to work contexts. Attention network optimization. The brain's attention networks, which govern focus, distraction management, and cognitive switching, are fundamental to learning agility. Neuroscience research demonstrates that targeted attention training techniques can significantly enhance a leader's ability to focus on relevant information, filter distractions, and efficiently shift attention between tasks. Posner and Rothbart. 2007. Effective approaches include single-tasking protocols. Establish 25 to 50-minute focused work blocks, based on the Pomodoro technique. Remove all digital distractions during deep focus periods. Document emergent thoughts in a designated capture tool. Without switching tasks. Attention switching rituals. Create 2 to 3 minute transition routines between different cognitive tasks. Use physical movement or environment changes as attention reset triggers. Practice mindful awareness of attention state before beginning new tasks. Goldman Sachs implemented an attention optimization program for its senior leadership team after internal analysis showed executives were spending an average of only 3 minutes on any task before being interrupted. The company created focus zones with strict no-interruption protocols and trained leaders in attention management techniques. In high-intensity deal periods, leaders now use structured 45-minute focused work blocks followed by 10-minute communication windows. Within 6 months, the program reduced decision errors by 21%, decreased average deal analysis time by 14%, and improved employee satisfaction with leadership communication clarity by 37%. Stress regulation for optimal learning states. Neuroscience research has established that stress significantly impacts the brain's learning capacity. Moderate, short-term stress can enhance attention and memory formation, while chronic or excessive stress impairs prefrontal cortex function and hippocampal learning processes. Arnston. 2015. Implementing structured approaches to stress regulation creates neurobiological conditions conducive to learning agility. Effective approaches include physiological regulation techniques. Train heart rate variability coherence through breath control, 5-second inhale, 5-second exhale. Implement brief physical movement between cognitively demanding tasks. Practice progressive muscle relaxation before complex learning activities. Cognitive reappraisal methods teach structured reframing of challenges as growth opportunities. Use benefit-finding protocols to identify positive aspects of stressful situations. Implement perspective-broadening questions during problem analysis. Mayo Clinic developed a comprehensive stress regulation program for its clinical leadership team to enhance learning capacity during its large-scale digital transformation. The program integrated physiological monitoring technology with targeted micro-interventions throughout the workday. Leaders were trained to recognize their personal stress signatures and apply specific regulation techniques calibrated to their stress profiles. Wearable devices provided real-time biofeedback, helping leaders identify optimal learning windows. The initiative resulted in a 32% improvement in new technology protocol adoption, a 28% reduction in reported burnout symptoms, and a 24% increase in self-reported learning capacity during change implementation. Social brain activation for collaborative learning. The human brain is fundamentally social, with dedicated neural systems for social cognition, empathy, and collaborative learning. Research in social neuroscience demonstrates that learning in properly structured social contexts activates multiple memory systems simultaneously and enhances perspective-taking capacity, a key component of learning agility. Lieberman, 2013. Effective approaches include structured knowledge sharing protocols. Implement 15-minute weekly learning exchanges, where leaders teach recent insights. Create cross-functional learning triads with complementary expertise domains. Use guided peer coaching with neuroscience-informed question sequences. Psychological safety practices. Train leaders to respond to mistakes with curiosity rather than judgment. Normalize knowledge gaps through leader vulnerability modeling. Implement uncertainty naming practices in complex problem-solving. Unilever implemented a social brain activation program across its global leadership team to accelerate cross-cultural innovation capability. The company created learning cohorts of 6 leaders from different regional markets who engaged in structured knowledge exchange protocols twice weekly. Each cohort followed a neuroscience-informed collaboration methodology that alternated between divergent thinking, perspective sharing, and convergence synthesis. Over 18 months, the program generated a 41% increase in cross-regional innovation initiatives, reduced new market entry mistakes by 26%, and improved leader confidence in adapting to unfamiliar cultural contexts by 47%. Metacognitive strategy development. Metacognition, the ability to think about one's own thinking, is central to learning agility. Neuroscience research shows that explicit metacognitive training enhances the brain's executive function networks and increases cognitive flexibility. Fleming and Dolan, 2012. Leaders with strong metacognitive skills demonstrate superior ability to recognize knowledge gaps, select appropriate learning strategies, and transfer knowledge across domains. Effective approaches include learning strategy inventories. Assess leaders' current learning approaches against neuroscience-validated methods. Match learning strategies to specific types of leadership challenges. Build personalized metacognitive toolkits aligned with cognitive strengths. Reflection protocols. Implement structured post-experience reflection using fixed question sequences. Create learning journals with prompts targeting different metacognitive skills. Establish peer reflection partnerships with guided dialogue frameworks. IBM created a metacognitive development program for its senior technical leaders to enhance their ability to navigate exponentially changing technology domains. The company developed a proprietary Learning Strategy Navigator tool that helps leaders match specific learning approaches to different technical challenges. The system incorporates brain-friendly learning techniques with artificial intelligence that identifies patterns in individual learning preferences. Leaders engage in weekly guided metacognition sessions to evaluate strategy effectiveness and make adjustments. This approach has reduced technical skill acquisition time by 34%, improved cross-domain knowledge application by 41%, and enhanced leaders' confidence in tackling unfamiliar technical challenges by 53%. Building long-term learning agility capability. Neurobiological capacity building. Sustainable learning agility requires developing the underlying neurobiological systems that support brain change and adaptation. Research demonstrates that specific lifestyle and work practices directly impact the brain's physical capacity for neuroplasticity through mechanisms including BDNF production, myelination efficiency, and network connectivity. Merzenich et al. 2014. Organizations can support neurobiological capacity through sleep optimization programs that educate leaders about sleep's critical role in memory consolidation and provide practical tools for improving sleep quality. Physical movement integration into the workday, as research shows that aerobic activity increases BDNF levels and enhances neuroplasticity for several hours, Kotman and Berchtold. 2002. Cognitive challenge protocols that systematically expose leaders to novel problems slightly beyond their current capabilities. Creating productive neural adaptation stress. Nutritional support focusing on compounds that support brain health and neuroplasticity, including omega-3 fatty acids, antioxidants, and adequate hydration. Attention ecosystem design. Learning agility flourishes or falters largely based on the attentional environment in which leaders operate. The brain's limited attentional resources must be protected through deliberate ecosystem design that aligns organizational practices with attentional neuroscience principles. Gazzoli and Rosen. 2016. Key elements of attention ecosystem design include communication protocols that batch information delivery. Establish no interruption periods and create clear message urgency guidelines. Physical and digital environment optimization including distraction-minimized spaces, notification management systems, and attention-preserving meeting structures. Cognitive load assessment of leadership roles, with redesign of responsibilities to create sustainable attentional demands aligned with brain limitations. Recovery rhythm establishment through workday structures that alternate focus and diffuse attention modes, allowing for natural brain oscillation between concentrated and creative states. Learning culture neurodynamics. Organizational culture creates a powerful context that either enhances or inhibits the neurobiological conditions for learning agility. Research in cultural neuroscience demonstrates that social norms, leadership behaviors, and reward systems directly impact the brain states associated with openness to learning and willingness to change. Mental models. Han et al. 2013. Critical elements for a brain-friendly learning culture include curiosity promotion through leadership modeling, recognition systems that reward question asking, and normalization of not knowing as a valuable state. Psychological safety reinforcement via consistent responses to mistakes that emphasize learning rather than blame. Creating the neurochemical conditions where the brain remains in exploratory rather than defensive states. Status threat minimization in learning contexts through carefully structured feedback approaches. Peer learning formats and removal of performance evaluation from developmental spaces. Progress recognition practices that leverage the brain's reward systems by celebrating learning process milestones rather than just performance outcomes. Stimulating dopaminergic reinforcement of learning behaviors. Conclusion. The integration of neuroscience insights into leadership development offers unprecedented opportunities to enhance learning agility, a capability that distinguishes adaptive leaders in volatile environments. The evidence presented demonstrates that targeted neuroscience strategies can significantly improve both the speed and depth of leadership learning capacity when systematically applied. Organizations implementing these approaches have realized substantial benefits including accelerated innovation, improved change adaptation, enhanced decision quality, and stronger talent retention. Individual leaders experience reduced stress, improved cognitive endurance, greater psychological safety, and more satisfying learning experiences. The most effective approaches combine multiple neuroscience principles, optimizing neuroplasticity mechanisms, enhancing attention networks, regulating stress responses, activating social brain systems, and developing metacognitive capabilities. For sustainable impact, these interventions must be supported by long-term neurobiological capacity building, attention ecosystem design, and cultural neurodynamics that create brain-friendly learning environments. As business complexity continues to accelerate, organizations that systematically apply these neuroscience principles will develop leadership teams with superior learning agility, providing a decisive competitive advantage in rapidly changing markets. The science of the brain has become an essential foundation for the art of leadership.